I unmuted myself. Good morning, guys. Welcome to today's Kahoot. Before we get going, what I'm going to do is just do a quick review of a few pieces that are going to be in the quiz today, because I know a few people have asked for it. Just because they've, I put in a few questions that do surprise people. So, yeah, that's what I'm going to do first. So, if you've got a pen and some paper handy to make a few notes, that would be good. Otherwise, well, I'll just give you a minute to do that whilst I change onto that screen. So, let's bring that up. There we are. Right, so... Right, that's what I want. Okay, so just going to review a few bits and pieces on magnetic fields, and going to use PowerPoint. As you can see, it's below me. It's below me here, and go through some stuff that's going to be in today's quiz. So things I'm going to go over then. So I'm going to go over magnetic field patterns really quickly. Going to go over Fleming's left-hand rule. And then FLEMING'S, the equation that goes with it. If you've got any questions on this stuff, I have got the live chat coming up in front of me. So if you've got questions whilst I'm going through stuff, you can put them in the live chat, and I'll try and answer them as we are going along. So, right, magnetic field shapes then. So, these are the three magnetic field shapes that could be in questions that we're expected to know for GCSE and for A-level. For our bar magnet then, right, these lines, magnetic field lines. The black lines on these are called magnetic field lines. They flow always from north to south, and the closer they are together, the stronger the magnetic field is. So you can see in this middle one, in the solenoid, these lines here really close together. This is the strongest field. Out here, where they get more spread apart, those feel that field's not as strong. Now, the strength of magnetic field is called magnetic field strength, but it is also called magnetic flux density, because sometimes these lines are called flux lines, lines of flux. And we've just said the closer they are, the stronger the field. So it's called magnetic flux density, because more lines in the same area equals a stronger field. Okay. Now, magnetic flux density, magnetic field strength, we call B field for short. Like I said the other day, B, don't know why it's called B. There is no rhyme or reason to it. It's just what they've gone for. We measure it in Tesla, after Nikola Tesla, who did quite a lot of work in this area. So Tesla, or if you just shorten it down, a capital T. Now, for a bar magnet, it's dead easy to tell which way the field lines go. Alright, for bar magnet, they always flow from north to south. So whichever way the arrow's going, that they're coming out to the north, going to the south. That tells you which way they are. But for a solenoid or a current carrying wire, it's a little bit trickier because they don't have north and south marked on them. And if anything, for a current carrying wire where they're going round and round in circles, there is no obvious north and south pole. So we use something called the right-hand corkscrew rule. Okay. Now, to do this in a wire is dead easy. As on the diagram, you place your thumb in the direction of the current, and the way your fingers curl round, so if we do this towards the camera, thumb in the direction of the current, and the way your fingers curl round shows you which way round the magnetic field goes. So in our diagram here, we have our thumb, our current going up, so our thumb points up, and the current goes round. Okay, and our field lines go, our field lines round. Field lines go in the same direction as our fingers curl round. Okay, for our solenoid then, solenoid's a little bit trickier. So for a solenoid, we do it in the opposite direction. So For a solenoid, here's our solenoid. You place your fingers, they curl round in the direction that the current itself is going in the coils. Okay, so in this diagram, the current is coming in here. It's going round the coils, go round and round and round like this. So we curl our fingers in the direction it's going. So it's going this way around those coils. And our thumb then, going around like this, and our thumb points towards the North Pole. Okay, so the current is going this way round, fingers curl round, and it points towards the North Pole. Alright, so it's in this diagram here, you can see that the current comes in, it coils this way round. So in the diagram we've got below us, what you're going to have is the coils coil that way, and your thumb points towards the North Pole, like so. Okay then. Yeah, there we are. Direction of the field. Okay, Fleming's left-hand rule. I hope everybody is appreciating my my lovely drawing of a hand. So this is Fleming's left-hand rule. So you hold your hand. Again, let's just cut back to me. So Fleming's left-hand rule is you hold your hand like this. And your thumb is it shows the motion. Your second finger, sorry, your first finger, your index finger, that shows the magnetic field, and that points from north to south. And your second finger is the current, and that points from plus to minus. Okay, so just some quick ones here to get you started, if you want to practice them. Alright, so for the first one, we have got the field is going from left to right, so your first finger goes from left to right. The current is going back out the page, so you rotate your hand round, and the current is going back out the page. Your thumb then is pointing down. Your thumb is then pointing, hang on. First is field. Field is going this way, current is going that way. For me, the field should be going down. I put that arrow in the wrong place. Haha, good start. This is wrong. The arrow should be going this way, like so. It should be going down here. For this one, we're missing the magnetic field. So for this one, we are looking for which way this our field finger is going. Alright, so our current is coming out of the page, and our wire is going down, so our field is going from left to right, north to south, left to right. For this one, we're looking which way the current goes. So for this one, we go, field is going from left to right. The force is going up, so the current must be going back into the page. And then for this last one, again, this motion is wrong. This motion will be going up. Alright, so for this last one, the motion must be going up. Because if you look, the field is the same way round as the first one, but the current's going in the opposite direction. Like I said, these two arrows that are drawn in, these are wrong. It should be the two I've just drawn in. Okay, so the magnitude of the force. To calculate the magnitude, the size of the force. All well and good knowing the direction, but we also need to know the size of it. And we use this equation, F equals BIL. F is force, B is flux density, I is current, and L is length. Force will be measured in newtons, flux density measured in Tesla, and current measured in amps, and length measured in meters. Okay then, so let's go back to just me. Okay, so we're going to get going with the quiz very shortly. So I'm going to bring up Kahoot, and I'm going to give you 5 minutes to get going. So there's Kahoot. And you've got, guys, 5 minutes to get yourselves logged in, and then I'll be back to host the quiz. Okay, guys, so we've got about 30 seconds left. Till we get going. I can see it says that there are 19 people, I think it is watching, but only 13 players so far, so there must be a few of you who haven't got them in. So yeah, you've got about 25 seconds left. Just whilst you're getting ready, just before we start, towards the end of this quiz, you will need a calculator. So I would suggest you get one ready, just because obviously if you're using the one on your phone, it's going to get in the way. Alright, so, right, shall we get started? So, with 15 players, let's make a start. Okay, so yeah, all of these questions going to be on magnetic fields and things like that. So, first question. Put these SI prefixes in order. Starting with the smallest, working your way up to the biggest, please. Okay, yeah, well done to the 5 of you got that right then. So, in terms of our scores, well done, Barry McHawkin. Oh, right, okay, yes, okay, well done, Barry. Well done, hello, nearly got me. And well, in fact, well done everyone who's on that page. So, the poles on a magnet are called. So, what do we call the 2 poles on a magnet? Those are the options. Well done, guys. Pretty much all of you got it right. Yeah. So, yeah, north and south always calls north and south poles. So, yeah, well done to Barry, still top of the pile. Well done, Mr. Pest, who is the highest climber, up 9 places. Okay, quiz. Magnetic field lines then. Let's see who's listening. Magnetic field lines go from which one of these? Yeah, well done to the 7 people who got that right, who were listening earlier. So, yeah, magnetic field lines go from north to south. Let's see what that's done to the scores. Well done, Hannah, now top of the pile. Well done, all right, sir. Well done, Hannah Jones, and well done, Eliza. Well done, wash your hands. You're our biggest climber. Excellent. Right, so magnetic field lines are also called what? Well done, 9 people who got that right. Yeah, they're also called lines of flux. So yeah, lines of flux, magnetic flux density. We also call them lines of flux. Well done, the 2 Hannahs. Well done to Wash Your Hands. Well done to Hello. Well done to Leslie is Cute. Up 4 places. Right, question 5. Magnetic field strength is also known as... which one of them? Flux volume, flux density, flux strength, flow density. Well done to 9 people who've been listening. 8 people who've been listening. Yeah, they are magnetic flux density, or it is also known as magnetic flux density. Well done to Hannah Jones. Well done to Wash Your Hands. And well done to 1, 2, 3 Evel, are now our top 3. Well done to Hannah as well with your answer streak of... oh, wrong button. Right. So, the unit of magnetic flux density is measured in watt. So, you've got to type in your answer here. Yeah, well done to those 5 people. Tesla, hopefully that picture was a clue. That is a picture of Nikolai Tesla. And yet one person who put in capital T, that's acceptable as well. I didn't say I just needed it in the words. So what's that done to our scores? Well done to Wash Your Hands, who's now in 2nd place. Well done to Hannah, who's in 3rd. And Barry's back into our top 4. Up 3 places, MAW. Well done. Okay, so in the diagram, the closer the lines of flux, the weaker the field, the narrower the field, the stronger the field, the bigger the field. Okay then, guys. So, yeah, closer lines flux, the stronger the field. Density, remember, it's called magnetic flux density. So more lines in a given area or volume, stronger that field. Well done to those 11 people. So well done to Hannah. You're on fire with 6 correct answers. Well done, MAW. Now into our top 5. So, question 8. Okay, put these steps in order to tell which way the magnetic field goes around a wire. Diagram's there to help you. Alright, so it looks like there might only be one person who got that right. This is the order then. So we decide which way the current flows. We put our thumb in the direction of the current, right hand, and close our fingers to make a fist, and the way you curl your fingers is the direction of the field. So, well done to Hannah. Looks like you were the only one who got that right. Oh, massive marker. Looks like you might have gone up 3. Okay, so in the diagram, which direction do the field lines go? In this diagram, I've got a wire in the middle, here, and these other two are field lines. Which way do they go? Interestingly, nobody got that right. Yeah, it should have been anti-clockwise. So, the dot. Now, this is perhaps something I didn't go through earlier. Okay. The dot then tells you that the current is coming out of the page. The current is coming towards you. And you curl your fingers round. And when you curl your fingers round, they will curl round anti-clockwise. So those field lines will go round anti-clockwise. So, what's that done? Nobody got it right, so it's not going to do anything to our score. All right, in this diagram, which way must the current flow? That should say, which way must the current flow to produce the field in the diagram? Not move that one. I want to move that. Well done to the 8 people who correctly guessed or worked it out using their fingers. So again, remember this is our right hand. You curl your fingers round which way the current is flowing. Thumb gives you the field. Not that's done very much to our top 5. All right. Which hand do you use to find which way a wire moves in a magnetic field? So which hand? Which hand? Yeah, well, I'm 5 year old left hand, Fleming's left hand rule. Interesting chat about socks. Until it turned cold the last couple of days. No, I agree with you. What's the point in socks? There we are. Right, so if you're not wearing shoes, why wear socks? Well done to Barry, who's gone up into the top 3. Okay, when you're using Fleming's left hand rule, here's my lovely hand I drew. So, using Fleming's left hand rule, your thumb is what? What does your thumb tell us? Okay, so these were the acceptable answers. Thrust, motion, force. Well done to the one person who got motion. That was nobody in the top 5. Oh dear. Okay, right. So When using Fleming's left-hand rule, your first finger is what? What's your first finger? What does this first finger? Yeah, field, magnetic field, B field. Well done to the two people who got that right. First is field. Well done to Eliza then, who's getting into our top 5. Okay, so quiz in the diagram below. Which way will the wire move? So we're now using Fleming's left-hand rule. So you need to hold your hand in the right direction, and that will tell you which way this wire will move. Okay, so just put me on the screen. Right, so yeah, 2 of you got that right, away from you. So you hold your left hand, you place your first finger going from north to south. So your first finger going from north to south. So like so, from north to south. Your first finger, sorry, going from north to south. Whichever way, there we are. Your second finger shows the current, and your thumb then says it's going to go away from you. Okay, so not done anything to our top 5. Okay, so a wire has current flowing from north to south. The wire moves east. Which way is the magnetic field pointing? Okay, so a lot of people put left. So again, with your hand, so if I bring up the compass just to help this. So the current is flowing from north to south. So your first finger needs to go from north to south. The wire moves east, so the force is east, which means that your index finger is pointing down. Take care of those compass points. Does throw some people when they start to do that. Okay, so question 16 out of the 20 we are doing. When calculating the magnitude of the force on a wire, what units do we use? Yeah, well done, 7 people. Yeah, newtons, Tesla, amps, meters. Those are the ones we need to work in. So, when we're doing some questions coming up, take care. The questions, the next 4 slides are all going to need that formula. So take care to make sure you're always in newtons, Tesla, amps, meters. Well done, Evo, up 3 places. Well done, MAW, up into the top 3. Okay, so from this point forwards, all right, double points. All right, last 4 questions. Do some double points. These are a bit harder. They're all involving calculations, so you will need something to probably help you with those calculations. I wouldn't suggest you do them in your head. Okay, so double points. What is the force? So have a read of this question. A 2 meter long wire is placed in a magnetic field of 0.25 Tesla. What is the force on the wire if the current is 1.2 amps? Okay, so yeah, well, on to the 7 people, it's 0.6. If you multiply 2 by 0.25 by 1.2, you get 0.6. So, well done to Hello, our biggest climber, up 3 places. It's getting tight at the top. Right, question 19. Again, double points. So, what is the magnetic flux density? So we're looking for B now in that equation. If 2.5 meters of wire has a current of 2 amps and experiences a force of 6 newtons. Okay, so well done, guys, to the 2 people who got that right. Yeah, 1.2 Tesla. I don't want the picture. So what you're going to do is do 6 divided by 2.5 times 2, and you get 1.2. Well done. The people who got 0.83, you did the sum the wrong way up. All right, well done, Evo. Biggest climber again. Okay, so double points, 2 to go. 85 centimetre piece of wire experiences a force of 48 millinewtons. It's in a magnetic field of 0.34 Tesla. What is the current? So take care with the centimetres and the mini Tesla. Well done to the one person who got 0.166 amps. The people who got 1.66, you weren't careful of the centimetres and the milli. You've just multiplied the numbers there rather than converting them into what they should have been. So that's not done anything to our top 5. Right, last question then. So this is more involved. You've got more time because it's a trickier question. So you've got a length of wire 3.4 meters. It's experiencing a force of 5.4 newtons. It's got a magnetic field of 0.34 Tesla. If I measure the voltage across the wire, I get 1.2 volts. What is the resistance of the wire? Okay, so you're going to need to do 2 calculations here. One, to find the current in the wire using F equals BIL. The second, once you've got the current, use the equation here. Resistance is voltage divided by the current you've got to work out the resistance. Now, don't worry about units because I know people struggle to put in the ohm symbol. But good luck. Oh dear. Okay, so to do this question then, what you do, let me grab a pen. There's a pen. Okay, so to do this question then, let's just move some stuff around there, and we'll put the camera down on the piece of paper. So here's our piece of paper. What I will just need to do is flip this camera. So, and flip it vertically. Let's just flip it again. Flip it vertically. There we go. Right, so first things we do then. So we have F equals BIL. So we want I, so we have I is F over BL. So that's 5.4 divided by 0.34 times 3.4. And that will give us our current. Now the current, if I remember rightly, is about 4.7 amps. Somewhere in those regions. It's slightly off from that, but that's close enough, that will do. Okay. And then we do our resistance is 1.2 divided by our current 4.7, and that gives us an answer of, when you put it in your calculator, you actually get the green value down here, but these are all acceptable roundings that you could have used. Hopefully that helps with that. And let's see who's won then. So let's go back to looking at me. And let's flip myself the right way round again. There we go. Right, so let's see what that's done to our scores. So, well done with 10 out of 21. MAW, you're in 3rd place. Well done to 2nd, 9 out of 21. Wash your hands. And with 9 out of 21, but answered them quickly. Hannah Jones, well done, top of the pile. Like I said, if people want house points, let me know who was who on there with their username. I can give out some house points. Let's just move that camera so it's looking at me a bit more. So, let's go to the camera. There we are. Right. So, going forwards, this is going to be probably more the model of what I want to do going forwards. Do a review of something. I'll let you know what topic I'm doing, and then do a Kahoot straight after. So, starting next week, similar idea. So, Tuesday, doing some stuff on circuits again. So, going to do a bit of a review. Do that, and then a Kahoot afterwards. Thursday, going to look at electromagnetic induction, finishing off the workbook that you guys should be working on, and then do a Kahoot based on what we did. What I will do is I will tweet and email when the Kahoots are starting on both days if you don't want to watch the review beforehand. Alright, so guys, stay safe. Follow the advice. It won't be long, hopefully now, till schools reopen and we get back to normal working. All right. I will see you guys Tuesday. I'll be hosting another one of these Tuesday then.